Okay, so we have this Ethernet technology, which used to have one wire, and everybody had to sort of share that medium. And there were some issues about if you're transmitting, when do I transmit? You know, the Aloha network, all these strategies for not trying to all broadcast at the same time and ruining everybody else's transmissions. So we had this sort of evolution of these point-to-point communication systems. So now modern Ethernets are not one big cable that goes to every drop in the building, but instead we have nothing but point-to-point communications and active electronics that takes packets from one wire, buffers it up, and then puts it on another wire. So nowadays everything is sort of point-to-point. And in fact, in modern systems, pretty much single driver, single receiver, point-to-point communications is how everything works. It's how you communicate to your disk, it's how you communicate to your graphics card, it's how you communicate with your memory system, it's how you do pretty much all communication are these highly engineered, very high-speed, point-to-point communication systems. Okay. So we used to have these buses. Now we basically have nothing but these unidirectional serial point-to-point links. This is what PCIe is, and that's the primary interconnect in your computer these days. A single differential pair going one way and coming back, so sort of symmetrical communication. If you want, and we have individual clock recovery on in each direction and stuff like that. So it's this big high-speed serial, and as I say, these are running now at multiple gigahertz. So it's these tiny little 10 gigabit networks over these single wires from one of your chips to the chip next door. We want more bandwidth than we can get over that, although that's sufficient for most things. Things like video, it trivially fits into such a one-wire communication scheme. But if we want really, really high bandwidth, we can gang them up. We can use them in parallel. And you see that now. So you have graphics cards that use 8, it says PCIe times 8 or times 16. What that's telling you is it's using 16 of these channels in parallel. And it takes the big message, breaks it up into 16 little messages, transmit them over these 16 little networks. And then there's big electronics that assembles it all at the far end. It sounds complicated. It is. There's a lot of mechanism that goes into that. And it takes a lot of transistors to do that. Happily, transistors we got lots of. Okay, so in today's computers, everywhere you look, there are these very high speed. So this is a modern diagram of a system that you could have bought probably last year, but it's all about these very high speed point-to-point links. Okay, so Sauron would be happy. There's one thing that we use these days to connect up all the parts of the CPU. And away we go. Okay, this is just a little bit of detail about some of the numbers that are associated with the actual signaling across the PCI Express. Notice that there's several layers of packetizing that happen. Right, we start with our original message down here, which you might want to say, "This is a memory address, Mr. Memory System. Please, return that to me," or "Please, Mr. Graphics Card, draw a line from here to there." That's packetized and broken up into a whole sequence of packets, and so we have a sequence number for the packet. This whole thing is protected by a CRC, so we can tell if the payload has been corrupted. We then stick basically a synchronizing sequence at the stop and the end, so the low-level electronics can synchronize up the clock recovery and figure out when a packet starts. So